Welcome to the new era of video creation with Bayo Z8. Today, we will discuss the scalable machine learning pipeline. Question: how would you approach building a scalable machine learning pipeline for training and serving large models? What are the key components and challenges you would address? A machine learning pipeline is an end-to-end workflow that automates the process of data collection, pre-processing, model training, evaluation, and deployment. As models and datasets grow, scalability becomes essential to ensure the system can efficiently handle larger volumes of data and higher demand. Scalable machine learning pipelines are vital in industries such as e-commerce, finance, healthcare, and autonomous systems, where real-time predictions and large amounts of data are commonplace. The goal of building a scalable pipeline is to ensure the system can support ongoing model updates, high-throughput predictions, and minimize latency, even as demand grows. The key components of a scalable machine learning pipeline include data ingestion. Efficient collection and storage of large datasets are crucial. This can be achieved by using distributed systems such as Apache Kafka for real-time data streaming or Hadoop Spark for batch processing. Data pre-processing: clean, normalize, and prepare the data for training. This often involves steps like missing value imputation, scaling features, or even feature extraction. These steps must be scalable and can be handled using Apache Spark or cloud-based platforms like AWS Glue for distributed data processing. Model training. For large models and datasets, distributed training methods like data parallelism and model parallelism are necessary to speed up the training process. Frameworks like TensorFlow, PyTorch, and Horovod can help with distributed training. Model deployment. Once a model is trained, it needs to be deployed in a production environment. This includes serving models in real time via APIs or batch processing, ensuring low latency and high availability. Efficient data ingestion and storage are foundational to any scalable ML pipeline. The primary challenge is handling large-scale data, whether it's arriving in real time, streaming, or in batches. For real-time data, tools like Apache Kafka are often used to stream data into the system. For batch processing, data can be collected using distributed storage systems like AWS S3 or Google Cloud Storage. Ensuring fault tolerance and data consistency is crucial. These systems should be designed so that even in the case of failures, data is not lost, and the system can continue to process without significant disruption. Scalability needs to be built into the storage layer to handle large datasets and variable loads. Data pre-processing is often one of the most resource-intensive parts of an ML pipeline, especially when dealing with large datasets. It involves tasks such as cleaning, normalizing, and feature engineering. Parallel processing is key to scaling pre-processing. Frameworks like Apache Spark and Dask allow for parallel computation across multiple machines, enabling the processing of large datasets efficiently. Distributed pre-processing frameworks like Google Dataflow or AWS Glue can help handle pre-processing tasks across distributed environments, minimizing bottlenecks and latency in the pipeline. Proper resource management is also essential to ensure the pipeline can scale dynamically, especially when processing large data batches or streaming data in real time. Learning pipeline. Training large models often requires substantial computational power and efficient resource management. Distributed training can be achieved through data parallelism, splitting data across multiple GPUs, and model parallelism, splitting the model itself across different devices. This allows the training process to be accelerated and scaled across multiple machines. Cloud-based GPUs or TPUs, like those from AWS, Google Cloud, or Azure, can be used to offload the intensive computations involved in training large models. Horovod is an open-source framework for distributed deep learning that integrates well with TensorFlow and PyTorch to make multi-GPU training more efficient. Kubernetes can be used for efficient resource allocation and managing distributed training jobs across clusters. Hyperparameter tuning is an essential part of building machine learning models. It becomes even more challenging when dealing with large models and datasets. Traditional grid search or random search becomes inefficient at scale. Therefore, tools like Optuna, RayTune, and HyperOpt offer automated ways to search for the best hyperparameters using Bayesian optimization or other advanced techniques. These frameworks also allow for parallel execution, where multiple hyperparameter configurations can be tested at once, speeding up the tuning process. However, hyperparameter tuning can be time-consuming, so it is crucial to manage resource utilization effectively to avoid over-provisioning. Once a model is trained, it needs to be served for real-time predictions. Model serving at scale requires low latency responses and high availability. Scalable APIs can be used to serve the model's predictions, with frameworks like TensorFlow Serving and Torch Serve providing efficient, production-ready serving environments for machine learning models. Load balancing is critical to ensure that incoming requests are distributed across multiple instances of the model, preventing bottlenecks and ensuring high availability. Kubernetes can be used to automate scaling and manage the serving infrastructure, ensuring the system scales in response to demand and maintains reliability. In real-time systems, latency is a crucial concern, as predictions need to be delivered in near real time. Reducing prediction latency can significantly improve the user experience and system responsiveness. Model architectures should be designed to minimize latency, such as using smaller or more efficient models where feasible. Techniques like model quantization, reducing precision, distillation, transferring knowledge from a large model to a smaller one, and compression can be used to reduce the size of the model and make predictions faster without compromising much on accuracy. The trade-off between latency and accuracy must be carefully considered based on the use case. For some applications, slightly lower accuracy might be acceptable if it significantly reduces latency. After deployment, the model must be continuously monitored to ensure it is performing well. Over time, models can experience drift, where their predictions become less accurate due to changes in the data or environment. Real-time monitoring tools like Prometheus and Grafana can track the performance of the model in production. Model drift detection methods, including statistical tests or comparing recent predictions to expected outcomes, can help identify when the model needs to be retrained. Automated retraining pipelines can be set up to periodically update the model with new data, ensuring it adapts to any changes in the data distribution. Building a scalable machine learning pipeline comes with several challenges. Data quality. High-quality data is essential for training accurate models. The data should be clean, accurate, and free from biases that could affect model performance. Cost. Large-scale machine learning can be computationally expensive. It's important to balance computational resources with the needs of the system to avoid unnecessary costs. Compliance and security. Privacy concerns, especially with sensitive data, e.g., in healthcare or finance, must be addressed to ensure compliance with regulations like GDPR or HIPAA. Scalability. The system must be able to scale efficiently as user demand and data volumes grow. This includes scaling infrastructure for training, serving, and storing large datasets.